All right, in this video, I'm going to go over section 2.3, normal probability distributions. Sampling distributions in estimator. Okay, sorry. So now we're going to focus on the sampling distribution of statistic. So as you can see that here, instead of working with the values from original population, we want to focus on values of statistic. What is statistic? Characteristic of a sample space, sample data. For example, sample means or sample variance, sample standard deviations, or sample proportions. Okay, so so now the first one, we have to look at the first one. We're gonna learn the behavior of sampling distribution. So what's the sampling distributions? So the sampling distribution is this. We're gonna the the uh, s- uh, select the samples, not just one times, but many times. Okay, so the for example, we want to get the 100 samples or 1,000 samples, and then we're going to find out. We're going to calculate statistic for each samples. Then we can find out some kind of pattern or behavior of these statistics. Okay, so we see when samples of same size are taken from the same population, the following two properties apply. The first one, sample proportions tend to be normally distributed, and then normal distributed what does that mean? So sample the I mean the probability distribution of sample proportions has a bell shape. Okay, and then in case of the continuous random variable, or in case of the discrete random variable, the even the in case of that the we deal with a discrete random variable, then the when you draw the histogram of the probability distribution of sample proportion, then we're gonna the shape is like the bell shape. Okay, so that's the meaning of the first statement. And the second one, the mean of sample proportions is the same as the population mean. This is really important, and then the really useful kind of property behavior. I mean, so mean of sample proportions is the same as the population mean. Okay, so now we're gonna the look at this one later again. So now I told you sampling procedure. Look at this. Randomly select the n values and find the proportion p hat for each sample. So you see the p hat. So keep in mind is that symbol p hat always used to represent the to denote the sample proportion. Keep in mind this. So not just one sample, okay? Not just a single sample. We're gonna the construct the many samples. Okay, sample one, sample two, sample three. It's possible, right? So we just select the n's values randomly, not just one time, just many times. Okay. So now then we can find the sample proportion for each sample from sample one through the, for example, sample 1,000 or sample 1,000,000. We calculate the sample proportion for each samples p1 hat, p2 hat. Okay. Now we're gonna take a look at the distribution of sample proportions. You see that? Okay, has a bell shape. So same sample proportion tend to have a normal distribution. Okay, so now the next one, this. What about the sample mean? Okay, so once we call once we get the this many samples. Okay, their sample size n, okay, and then we calculate the sample mean x1 bar, x2 bar. See here, x bar represents the sample mean, by the way. Then we draw the distribution of sample mean. Sample mean also tend to have a normal distribution. Okay. So now the last one. What about the variance? So you see s square. So a lowercase, excuse me, lowercase letter, excuse me, lowercase letter s represents the sample standard deviation. So S squared going to be sample variance. But sample variance doesn't tend to have a normal distribution. Instead of the skewed distribution. You see that the shape is not symmetric about the middle here, right? So it's skewed, right? So so now keep in mind is the behavior of sampling distribution. We're not talking about just one single sample statistic in one single sample. Okay, we're just talking about the statistic of sampling distribution. Sampling distribution means that the mean of sample means, okay, and then sample proportions of sample proportions, okay, or mean of I'm sorry, mean of the sample, the I mean statistics. Okay, keep in mind this. So now right there, for example, I mentioned about this, but let me mention about again. So the p at see the mean of in this case, it gives me mean of sample proportions. Okay, mean of sample proportions is tend to approach. As you can see that mean of sample proportion is the same as population mean. Okay, and then mean of sample mean is the same as the population mean. Okay, so now the right here. So we see sampling distribution of statistics. The sampling distribution of statistic, such as sample proportion or sample mean, is the distribution of all values of statistic when all possible samples of the sample size and are taken from the same population. Okay, so now then that we see that what sampling distribution means. Okay, sampling distribution is the distribution of statistics. Okay, statistics. So distribution of a statistic, for example, distribution of population sample means or distribution of sample proportions. Okay, that's the sample distribution of statistic. Okay, so the sample distribution of statistic is typically represented as a probability distribution in the format of probability histogram, formula, or table. So now let's see. And then the uh, well, let's talk about the sampling distribution of sample proportion. So now sampling distribution of the sample proportion is a distribution of sample proportions or distribution of the variable p hat with all samples having the same sample size and taken from the same population. The sampling distribution of the sample proportion is typically represented as a probability distribution in the format of probability, histogram, formula, or table. Now I mentioned about the notation of the proportions, but just keep in mind is the lowercase p represent denote the population proportion, p hat denote the sample proportion. Okay, keep in mind this. And that's the example today, by the way. So example one, sampling distributions of the sample proportion. Consider repeating this process. Roll a die 5 times and find the proportion of odd numbers. Okay, so roll a die 5 times means that we're going to get five samples, right? Sample data. So what do we know about the behavior of all samples proportions? They are generated as this process continue indefinitely. I'm sorry, it's roll a die 5 times doesn't mean that we get five sample. I'm sorry. So we're gonna repeat this one. Roll a die 5 times. We repeat this one. So for each experiment, rolling a die 5 times, we're gonna get sample, right? Sample data, right? So now then, okay. So in the first one, in a first time rolling a die 5 times. Okay, let's say that is sample one. Okay, so now then we can calculate sample proportions. Okay, how many the odd number we get in the first experiment, rolling a die 5 times. Okay, let's say 0.2. Okay, and the second sample. Okay, we're just we're gonna roll die 5 times one more times to get the second sample. Okay, and then we calculate the sample proportion. Okay, how many odd numbers we got out of 5 times. Okay, so we just calculate the sample proportions for each sample. Okay, now then as you can see that here we can draw the histogram of sample proportions, right? So maybe I'm not sure you can see this one, but let's see here the what So do you see that frequency about the more than 3,000, I think 3,200 times we got zero point 0.4 as sample proportions. Okay, so actually this histogram we get this one by, see that result, the figure shows a result from the repeating this process 10,000 times. Okay, so now the for 10,000 times more than 3,000 experiment, we got a zero point 0.4 simple proportions, and the points, and then also it's a 0.6. We got simple proportion of 0.6 and more than 3,000, right? So from here, you see that here, that you see the shape of the histogram looks like the normal distribution, right? So in the, as you know, we keep, I mean, increase the number of the experiment, then we're gonna get the more we're gonna get the histogram more, I mean, closer to the normal distribution, graph of normal distribution, I mean, bell shape. Okay, so now what about the let me see again. So now you see here the figures show that the sample proportions are approximately normally distributed because the values of 1, 2, 3, 4, 5, 6 are all equally likely. The proportion of odd numbers in the population going to be 0.5. You see that here, middle of the histogram going to be 0.5. Makes sense, right? So now the figure show that the sample proportion have the mean of 0.5. Yeah, makes sense. So you can see that the mean of sample proportion approach the population mean, which is 0.5, right? So now the next one, sampling distribution of sample mean. Okay, so this is really similar to the sampling distribution of the sample proportion. Okay, so sampling distribution of sample mean is the distribution of all possible sample means instead of sample proportions. Okay, so now then see okay, let's see example 2. Consider repeating this process. Okay, we're going to do same experiment in example 1. Okay, rolling a die 5 times, many times. Okay, so we're going to calculate the x bar. Okay, so now the see. So now we see find the mean x bar of the result. So by the way, what's the mean? I mean, let's figure out the population mean. What's the population mean? Then going to be what? In this problem, the population mean is going to be, should be 3.5, which is the same. I mean, it's just the same as the way we find out the average. Okay, of 1, 2, 3, 4, 5, 6, which is 3.5, right? So now the let's see. The we're gonna do, see that here the figure illustrate a process of rolling a die 5 times and find the mean of the result. The figure shows result from repeating this process 10,000 times. So we do the repeat rolling a die 5 times 10,000 times. So we're gonna get 10,000 samples, sample data, right? For each sample data, we're gonna calculate sample mean. Okay, some so certain samples, the sample mean gonna be 3.4. Other sample mean gonna be 4.4. Okay, and then we draw the histogram. To see here, you can see that the graph of the histogram is approximately um, normally distributed, right? The approximately the equal to the normally distributed normal distributions, right? So in the middle, it can be 3.5. So now the you see that the mean of sample mean, okay, see that mean of sample mean tend to approach the population mean. Okay, so now let's see. What about the sampling distribution of sample variance? So I told you we have seen that, right? Where is one? Sample variance. The sampling distribution of the variance is not normally distributed, right? So then that means what? The mean of what sample, the variance will not tend to approach what population variance. Okay, so see. Okay, so the sample distribution of sample variance, let's see, is the distribution of sample variance with all samples having the same sample size and taken from the same population. Okay, so now then the population. Oh, I mean, so what population standard deviation is this? Right? The population variance is going to be this. Okay, this is the formula. So what does that mean? Population standard deviation, the square root of the sigma, which means the sum of all of difference between x and the population mean square. Okay, so for example, the x is what? The values of random variable. Rolling a die 5 times, then for each um, you know the each time we get the number, right? Between 1 and 6, right? So for each time, for example, we got the 1 2 1 2 1 2, 4 3, for example. Then 1 2 1 2 4 3, these are x values. So 1 minus population mean, which is population mean going to be what? 3.5, right? So 1 minus 3.5 square plus, okay, 2 minus 3.5 square plus 1 minus 3.5 square plus, okay? So that's the meaning of sigma of x minus mu square. And then divided by n is the capital letter N is the population size of population, okay? And then variance is a square of standard deviation. So that square root, just taking square of the standard deviation, that square root gone. So we got this. And then now, but you don't have to memorize this formula, okay? So now then, see, distribution of the sample variance tend to be a distribution skewed to the right. Okay, skewed to the right means that the right tail is longer than the left tail. You see that? Back to the right here. You see that the right tail is longer than left tail. In this case, we say the graph is skewed to the right. What if just left tail is longer than right tail? Then we say that this graph is skewed to left. Okay, so see, okay, the sample variances target the value of the population variance. That is the mean of the sample variance is the population variance. That the expected value of the sample variance is equal to the population variance. Let's see. See here. So even though the distribution of the sample the variances tend to be distribution skewed to the right, then but sample variances target the value of the population variance. It means that the mean of the sample variances, mean of sample variances, uh, tend to approach the population variance. Okay, I was just confused with the sample standard deviation. Okay, so the keep in mind this: the mean of sample variances approach the population variance as the what as the number of experiments increases. Okay, so we see example 3, sample distribution of sample variances. Consider repeating this process, same experiment. We're going to do same experiment, um, the as the example 2 and 1 and 2. Okay, so what do we know about the behavior of all sample variances that are generated as this process continue indefinitely? So let's see. So pretty much is we're gonna do the same process as the what we did in example 1 and 2. Okay, so rolling a die many times, but in this case 10,000 times. So for each sample, we're gonna calculate sample variance. Okay. So now, how can I calculate sample variances? We saw the the formula, right? Now then, oh, so give me a second. So we haven't seen this formula, right? But keep in mind this: the formula population variance is not equal to, I mean, slightly different from the sample variance. Okay, so population variance is this, right? But the oh yeah, I cannot edit this one. But sample variance going to be s squared is equal to sigma x minus the x bar, right? Instead of mu, we subtract the x bar, which is sample mean square, divided by not n but sample size minus 1. Okay, so why this n minus 1, not n, in when you find the sample variance? That's beyond the subject. So I'm not going to cover that one. But keep in mind, it's population variance. The formula of population variance is not the same as the sample formula for finding sample variance. Keep in mind this. Sample variance is going to be sigma, I mean, s squared is equal to sigma x minus x bar squared divided by n minus 1. Sample size minus 1. Keep in mind this. So now using that formula, okay, so we can figure out sample variances. As you can see that we got the histogram distribution of sample variances, which is you see the graph is skewed to the left, right? So when you look at this one closely, then you see that the mean is not the middle, but because it's skewed right, so around the 2.9. Okay, so now that's the sample variances tend to have a skewed distribution, and then the sample variance is approach 2.9. Okay, as the number of the samples increase, then what sample variance close to 2.9. Okay, so and then now you see a couple of more new terminologies. Okay, so estimator. What's an estimator? Estimator is nothing but approximation in mathematics. So estimator is a statistic used to approximate, okay, or infer, estimate the value of population parameter. So normally it's hard it's um what it's not possible to, or it's really expensive to figure out population parameters. So we're gonna use sample to approximate population parameter. Okay, that value is called the estimator. Okay, so for example, in this one, mean of sample variances can be used as the estimator of population variance. Okay, so now unbiased estimator. Then you see, then there are two type of estimator: unbiased and biased estimator. Unbiased estimator is a statistic that target the value of the corresponding population parameter in the sense that the sampling distribution of statistic has a mean that is equal to the corresponding population parameter. So you know the unbiased estimator is the simply saying that unbiased estimator is kind of good estimator which target the value of corresponding population parameter. Okay, what a bias estimator? Bias, yeah. We're gonna just study three popular unbiased estimator we haven't seen, right? Sample proportion, and the sample mean, and sample variance. Okay, we haven't seen. We just saw that the statistic, right? So three statistic tend to approach the value of corresponding population parameter, right? So keep in mind, there's three statistic or unbiased estimators. Okay, and then what's a biased estimator? Median range standard deviations. Okay, they do not target the value of corresponding population parameters. Okay, sample median, sample range, and sample standard deviations don't target the value of corresponding population parameters. Keep in mind this. Okay, now you see sampling is conducted with a replacement because of these two very important reasons. When selecting a relatively small sample from a large population, it makes no significant difference whether we sample with a replacement or without replacement. Okay, so but sampling with replacement result in an independent events that are unaffected by previous outcomes, and independent events are easier to analyze and result in simpler calculations and formulas. So we'll see the some example of that one. Okay, next time. Okay, so next time I'm gonna cover section 2.4. Okay, and then we'll see the lecture note, lecture handout. Okay, so let me stop here.